Hi, everyone, and welcome to this next installment in our journey through algebra and pre-calculus. In this video, I want to talk about inverse functions, and this is going to be somewhat of a continuation of the last video in which we talked about, at least in the second half of that video, on compositions of functions. So f of g of x and g of f of x, plugging one function into another function. So we're going to see how that applies in the context of something new, in this case, inverse functions. So I've used this diagram, this image, previously when we were talking about functions in the beginning, in our introduction to functions. That was about 5 or 6, maybe 7 videos back. A function is like a machine. A function is an input-output machine. So a number goes in, so we could say the input, right? The input is, we're going to call that an x value. And then the function does something to it, and then it spits out some other number. It might be the same number sometimes, but usually a different number. And our output is a y value, which we're going to call f of x, or we've been calling f of x. Right? So for example, if this function, I'll use a different color, red. This is just an example, but let's say our function is f of x equals 3x plus 1. That function does two things. It takes an input. Let's say x equals, I don't know, -4. It takes the number -4, multiplies it by 3, and then adds 1. So the output would be y equals -11. Because we're evaluating a function, plugging a specific number in. So f of -4, 3 times -4 plus 1. Okay. So that's how functions have worked, and this is how they always work, an input-output machine. Now, some functions, not all of them, but some functions, whatever they do, can be undone. Whatever they do can be undone. This doesn't work for all functions, and we'll talk about which functions can be undone and which functions can't be undone. I think about when I say undone, I think about this in terms of being reversible. Can you reverse a function? Now, let's say there's another function out there. I'll use a different color. I'll say orange, g of x. So this is the g function. I'll label this g, right? This is the g function. And in this example, this is just an example, but let's say g of x is equal to, let's go with x minus 1 and all of that divided by 3. X minus 1 divided by 3. Well, let's take something from the previous video. Let's do g of f of x. All right, let's compose them. So I'm doing the f function first because we've already done that one. So f is going to be the inside function. So that's g of f of x. Well, you know what? Let's not do x. Let's use the number that we're working with. Let's say -4. Right, g of f of -4. And we already know what f of -4 is. That's what we did over here on the right. We got y equals 11 as our output. So f of -4 is -11. So that is g of -11. Oops. Let's go back to black. So now for the g of x function, I'm using x equals -11. So that's the input that's going into the g function. So what I'm just connecting these two functions. I'm connecting these two functions together. So this -4 went in, -11 came out. Now that -11 is going into the next function. We're going to use that as our x value for the next function. -11 goes in. Well, what do you get? What do you get when you put in a -11 into this g function? And I chose this specific g function as a very special function for this example. It actually is the only function. X minus 1 over 3 is the only function that will reverse the first function. It does exactly the opposite of the f function. So if we plug in -11 into the g function, that's -11 minus 1 divided by 3, which is -12 divided by 3, which is -4, exactly what we started with. So the output y equals -4. So the f function took a -4 and turned it into a -11. The g function took the -11 and turned it back into a -4. These two functions are called inverses of each other because whatever one does, the other one undoes. So the f of x equals 3x plus 1, and the g of x, oh, that doesn't look good. I'll do a little bit of, how about some green pen? So this f of x and this g of x are what are called inverse functions. When I say inverse functions, I mean inverses of each other. Whatever one does, the other one undoes. Now, when we start with the 3x plus 1, there's only one option for g of x. It had to have been x minus 1 over 3. I haven't talked about where that came from or how I came up with that in my head, but we're about to. We're about to. So this is the relationship. This is the relationship between a function and its inverse. Well, this over here, the second output back to y equals -4. Well, what is that? It's not actually a y value. It is g of f. Of x, in this case, -4. So in the context of the composition, f of g and g of f, these two functions, if you compose them, meaning you do one after another, you're just connecting them. It's a two-step process. First you use the one function, then you use the other function. If you always get back the original number, if you always get back the original number. So I started with a -4, and I want to cross out the -4. Start with the -4, and I end with the -4. Same number goes in, same number goes out. These two functions are called inverses of each other, and the notation we're going to use, is f with a little superscript -1 of x. So this is read f inverse of x. And this is read f inverse of x. So this is new notation here. This f negative 1, that's not an exponent. That is not f the negative 1 power. It's not a reciprocal. It's a label, and that label means inverse. A little negative 1 on the name of a function, that is the inverse of that function. So we wouldn't necessarily use g of x. We wouldn't necessarily use g of x. We would say f, let me go back. There we go. Sorry about that. We would go there we go. Okay, something was wonky with my pen there for a second. The g of x function, now we can call this the inverse of the f function. So we would say f inverse of x is equal to x minus 1 over 3. Okay? You can't start with the inverse. You have to start with the function, and then you could talk about finding the other function out there that reverses what that first function did. Doesn't always work. Not every function has an inverse, only specific types of functions. But if you determine that one type of function does have an inverse, we still need to talk about how to find that. Where did that x minus 1 over 3 come from? Okay. Here's our relationship. Again, from our previous discussion. If you compose a function with its inverse, so f inverse of f. So if you plug a function into its inverse, the order doesn't even matter. You get x. So on the previous slide, we used f of x equals 3x plus 1. We use g of x, x minus 1 over 3. And if you put them together, f of g of x, again, this was the previous video, the one right before this one. F of g of x would be f of x minus 1 over 3. You plug that into the f function, which would be, instead of 3x plus 1, it would be 3 times the g function, x minus 1 over 3 plus 1, which would be, well, let's see, the 3's will cancel. Times 3 and divide by 3. So we get x minus 1 plus 1, and the minus 1 and the plus 1 cancel, and we get x, exactly x, positive 1x. No negative sign, no addition, subtraction, no multiplication, no division, just x by itself. If you do this, if this gives this, right? If this happens, if you plug one function into another function and you get x, just positive 1x. In both directions, f of g of x, g of f of x, then f of x and g of x are inverses of each other. F of x and g of x are inverses of each other. And so we're using this idea of composition of functions as a tool to answer this type of question, right? Number one, here are two functions. Okay, here are two functions. We've got the f function. This is a yes-no question. Here's two functions. Are they inverses of each other, yes or no? Right? The answer is either going to be a yes or a no as your final answer? Yes, they're inverses. No, they're not. Well, we have to plug one function into the other function and see what happens. Right? F of g of x, or f of g of x, is equal to f of g of x, which is x plus 4 over 5. We're plugging the g function into the x. The whole g function is going into the x. So that's 4 instead of 4 times x minus 5. We get 4 times x plus 4 over 5 minus 5. So we can multiply the 4. And remember, that's 4 over 1. So 1 times 5 on the bottom. 4 times x plus 4. So that's 4x plus 16 on top. And then we've got a minus 5. I mean, just looking at this, this is not x. This is not x. So the answer is no. I mean, we could keep going. This is 4x plus 16 over 5 minus, we get a common denominator here and say 25 over 5. We could keep going. 4x plus 16 minus 25. So that'll give us a negative 9 over 5. This is not x, just x by itself. So the answer is no. We don't even have to do step 2. Right? If the step 1 gave us x, then we check step 2 in the other direction. If we also get x, then the answer is yes. But since we plugged one function into another function and we did not get x, the answer is no. These are not inverses of each other. Let's do one more of these. Let's do one more. Let's just switch up the functions, a different f and a different g. So next slide, problem number 2. Are these two functions inverses of each other, yes or no? All right, so here's the f function. Here's the g function. So let's do f of g of x, or g of f. It doesn't matter which one's first. Just check one. So that's f of g of x, which is f of, well, the g of x function is x to the 5th plus 5. Which means the entire g function is going in for x. Okay, so that is the 5th root of the g of x function. Minus 5. So replace the x with an x to the 5th minus 5. And very quickly we see plus 5 and minus 5 cancel. So that's the 5th root of x to the 5th, which is x. Check. And we plugged the g into the f, and we got x, just x by itself, positive 1x. So let's do the other direction. I'll switch to a different color, g of f. of x, and this is a good review of the previous video. G on the outside, F on the inside. So that's G of the fifth root of x minus 5. So that means we're taking all of this, the entire f function, and plugging it in to replace that x in the g function. Okay, so that's x to the fifth plus 5. So that will be the f function to the fifth plus 5. And pretty quickly we see the fifth power, the fifth root, they cancel. So we get x minus 5 plus 5, which equals x. So that's another green check. We get x both ways. So the final answer for this problem is the word yes. Yes, they are inverses of each other. Okay, so this is a way to test if two functions are inverses. Now, more generally, or there's more general of a problem, finding the inverse of a function. Oh, I shouldn't have said functions plural. That's bad grammar. The general method for finding the inverse of a function utilizes the fact that the inputs of one are the outputs of the other, and the outputs of one are the inputs of the other, and vice versa. So we're going to use that the outputs of the first function are the inputs of the other, so the domains and the ranges switch. So a good method, this is not the only method, but a good method for finding the inverse of a function. For example, this problem. Here's a function, f of x. Find the inverse. Find f inverse of x. Well, the inputs of one are the outputs of the other, and the outputs of one are the inputs of the other. So basically, between a function and its inverse, the x's and the y's switch. So that's going to be our first step. Swap the x's and the y's. And we're going to be working with an equation here. We're going to need both sides. So we're not going to use function notation. We're not going to use f of x equals. We're going to use y equals notation. We're going to use y equals notation. This way we could treat it like it's an equation and work with both sides of the equation. So step one, change every x into a y, change every y into an x. So instead of y equals 3x plus 1 over 5, it's x equals 3y plus 1 over 5. So that's it. That's step one. Change every x into a y, change every y into an x, and now solve for y. Solve for y. So this is something we've done previously. I think, don't quote me on this, but it was section in chapter P in the preparatory chapter before chapter 1. I think it was section 1, P.6, P.6 or P.7, solving a formula for a letter. So I have all the steps here, but I haven't shown my work. So let me just include a little bit of annotation here. X equals 3y plus 1 over 5. Let's solve for y. So the first thing we could do is multiply both sides by 5. Right, that'll cancel this 5. So now we're here. We have 5x on the left, 3y plus 1 on the right. We can minus 1 from both sides. That'll cancel the plus 1. And now we're here. 3y on the right, 5x minus 1 on the left. We can divide both sides by 3. That will cancel off the times 3. And now we're here. Five x minus 1 over 3 on the left and y on the right. And once you solve for y, that is your inverse function. That is your inverse function. And so that's how it works. In this case, f of x is equal to 3x plus 1 over 5. And the inverse, the function that reverses what that function does, is 5x minus 1 over 3. So in terms of what's our final answer is this guy right here. All right, so that is finding the inverse of a function. Now, I've talked about, or I've alluded to the fact that some functions don't have an inverse. Some functions don't have an inverse. Now, you either have to be told, like for in this next problem, the function f of x equals x plus 3 to the third power is 1-to-1. Right, so this is not something you have to think about here. This function is 1-to-1. Right, 1-to-1. This is a new term. So let's talk about that. So same question as before, find an equation for the inverse. Well, let's start with 1-to-1. First, only functions that are 1-to-1 have an inverse. If the function is not 1-to-1, it doesn't have an inverse. Now, what does that mean, 1-to-1? A function is 1-to-1 if is 1-to-1 if there's a lot of different ways I could say this. We could say if each y value is unique, or I could say if there are no repeated y values, or if each y value occurs only once. So let me say, I think I like 1-to-1 if no y values are repeated. If no y values are repeated. So I think the easiest way to explain this is with a couple of graphs, right? Let's look at two graphs here. The function y equals, or f of x equals x squared, and the function y equals, or f of x equals x cubed. Okay, x squared is a parabola centered over the y-axis, goes through the point 0, 0. And the function x cubed looks like, well, it looks like a parabola where the left half is actually reflected down and the right half is up. Okay. Y equals x squared is not 1-to-1. And the reason it's not is because if you plug in, let's say, an x value of 2, you get a y value of 4, because 2 squared is equal to 4. Also, if you plug in an x value of -2, you get the same y value of 4. So the number 4, the y value of 4 is repeated twice. And actually, infinitely many y values are repeated twice. The graph of the x cubed, no y values are repeated. So a visual test for whether or not a function is 1 to 1. If the function is not 1 to 1, then it does not have an inverse. It can't be undone. A visual test for 1 to 1 is what's called the horizontal line test. Horizontal, it's hard to read. Apologies for my terrible handwriting. One is the horizontal line test, because if you can hit a graph twice with a horizontal line, that means you have 2 points with the same y value. So if you can hit a graph with a horizontal line 2 or more times, 2 or more places, then that function is not 1 to 1 and does not have an inverse. Every horizontal line hits the graph of x cubed only once. So we could say, yes, it is 1 to 1. Yes, it is 1 to 1. So why? Why is y equals x squared? Why is that not reversible? Why can you not undo that function? Well, let me give you a easy example. Easy using just small whole numbers. Okay, so here's the domain. Those are the x values. Here's the range. Those are the y values. And here's the function f of x equals x squared. So a number goes in, you times it by itself, and a number comes out. Well, let's say the number that came out was 9. What number went in? What number times itself gave you 9? Well, there's no way. There's no way you can know. You could take a guess, but there's no way that you could know which number I plugged in to get 9. Because f of 3 is equal to 9. I could have plugged in a 3. But also f of negative 3 is equal to 9. So I could have plugged in a negative 3. So if I put a question mark here and say, okay, which one did I plug in to get 9? You have a 50-50 shot, but you can't tell me what number had to plug, which number I plugged into the function, right? So x squared is not reversible because the number 9 is coming from 2 different x values. 2 different x values. Now, if this was x cubed, and I said, well, I plugged a number into this function and I came up with 27. Well, there's only one way to get a 27. 3 times 3 times 3 is 27. Negative 3 times negative 3 times negative 3 is negative 27. So if I say I ended up with a positive 27, you know it has to have come from 3. And that's what inverse functions are doing. They're going backwards. They're starting with the output, going back to the input. Okay. This one's a real quick problem. Determine whether the function, which is shown on the graph, is 1-to-1. And the answer is yes, because any horizontal line is only hitting the graph once. So that's it. If you have the graph in front of you, the question of whether the function is 1-to-1 or whether it has an inverse, very quick. Very quick. Okay. Now, what does the graph of the inverse look like? Well, this is going back to the idea that the inputs of one are the outputs of the other, and the outputs of one are the inputs of the other. So the x values for a function are actually the y values of the inverse. The x values of the function, the x's of f of x, are the y's of f inverse of x. And the y values of the function f of x are the x's, the x values of the inverse, right? So the x's and y's flip-flop. The x's flip and the y's flop. So what that means graphically is that if we look at the line y equals x, which is a diagonal line, slope of 1, right? So this is the line y equals x. To get the graph of the inverse, and that's what we're trying to do here. Use the graph of the function, draw the graph of its inverse function. So on the graph down here, the blue one, that's f of x. And let's say this is going in both directions. The inverse, I'll use red, is the reflection over the line y equals x. So a mirror image over the line y equals x. So that part will flip down there. This part will maybe go up this way a little bit. So if you reflect this way, we've talked about reflecting horizontally over the y-axis. We've talked about reflecting vertically over the x-axis in the context of even and odd functions and symmetry of equations. We've talked about reflecting both or over the origin. Now, this is a fourth type of reflection, a reflection over the line y equals x. Gives you the graph of the inverse. Okay, so that is the graph of an inverse function. Now, one more. We've been dealing with functions expressed one way. As an equation, y equals a function of x. Here's a function defined for each of the functions has only 4 points. So the function f has 4 points. The first point is -2, 2. The second point is 0, 4. The next one is 1, 5. The next one is 6, -4. And the g function as well. Each pair is a point, -3, 0, and so on. So what we want to do is evaluate f inverse of g of 8. F inverse of g of 8. Oh, not x, 8. Okay, well, this is a good review. G of 8, the symbol G parentheses 8 is equal to the y value from the G function. When x is equal to 8. So saying G of 8 means what is the y value when the x value is 8? So we're only looking at this pair. When x is 8, the y value is -4. So that is equal to, don't want that one, this one. So let me do a little bit of color coding here. So G of 8 is the -4. Okay. So we still have the F inverse on the outside. So now we want F inverse of -4. We figured out inside the parentheses, the G of 8, that gave us -4. Now, what is F inverse of -4 mean? Well, that means the x value from the f function. The x value, not the y value. We're looking for the x value now. Everything changes, everything flip-flops when we start talking about the inverse instead of the original function. So the x value from the f function when y is equal to -4. And in this case, that's going to be 6. We don't need that point, or that point. And also, we don't need that one, or that one. For the f function, f inverse of -4 means start with -4 for the y value. What is x? In this case, x is 6. So that does it. This was more of a unique type of problem. But nonetheless, it's applying the ideas that we've talked about both in this video and in previous videos, evaluating functions, composing functions, and now in this one, inverse functions. All right, that does it. I think that's the end of the slideshow. Yep, that does it for this one. I hope this was helpful. And this is going to be the last video for this chapter. We're going to pick up in the next one with complex numbers. All right. Take care, everyone.